Just a minute. Cool. Cool. So hello, everyone. Good morning, and also good day for the folks outside of APAC community, outside of APAC region. So welcome everyone to today's APAC community call. So in today we have actually two agenda items. So first, we'll turn to Professor Jason Xu from Taipei Medical University to share a great OHDSI APAC news. I won't do any spoiler alert for now. And then we will have Gowtham Rao from Johnson & Johnson to demo on actually how to create cohort diagnostic tool for our studies. So without further ado, I will turn to Professor Jason Xu.
Hello, everyone. Thanks for letting me to have a chance to share the procedure about the preparation about the APAC Symposium today. And Lynn, would you like to help me to share the screen, share the slides?
No problem.
Okay. So based on our previous discussion about the steering committee, okay, of the APAC, OHDSI APAC. So this year's we will have a third OHDSI APAC Symposium in Taipei, in Taiwan. So that will be on-site and virtual combination style symposium, and the timing will be during November 12th and to 13th. Okay, so next one, please. Next slide. Yeah, so thanks for steering committee's support. And so that we have a chance to hold this kind of symposium. Okay, so here are the committee members. Okay, I would appreciate, okay, for your support. Next, please. So as you may know that Taiwan will enter into OHDSI network since 2020, which is the sixth country in Asia. Okay, so we can start to join this kind of network. That'll be very happy issue for us. Okay, so next, please. So here are the OHDSI Taiwan office, and we have some members in our group, and actually we are going to prepare for the symposium at the end of this year, and they help us to organize this kind of symposium, and we also need you guys help and support for to let us to achieve our goals for the conference. Okay, next, please. Yeah, so here is the draft of the basic program. We have not had the final decision about the very detailed arrangement about each part, but so this is the principle is that the first day will be the tutorial workshop, and we may have 4 tutorial, okay, during the first day. Okay, so tutorial that will be tutorial workshop in the same time. Okay, so during the morning, okay, we will have tutorials. Okay, and then in the afternoon we will have another two. Okay, for the day 2, that will be actual symposium. Okay, so we will have as the previous years, we will have in the morning we have some issues, some topics, and also in the evening, in the afternoon, we have the other topics and sharing from regional chapters, and also we'll have a panel discussion before the ending of the symposium. Okay, next one, please. So we plan to have an Eposter this year, and during the first day and the second days all day. Okay, so if you guys want, I mean the participants want to see the e-poster, we will provide this kind of chance. And the e-poster may be together with the 3-minute pre-recorded presentation, okay, with 3 slides. So there will be a chance to submit the e-poster, and then if the e-poster was accepted by the conference, the committee, they will have a chance to submit the final e-poster presentation slides before October 31st. Okay. Next, please. Before the end of October. Okay, so this is important dates. Okay, including the abstract submission deadline, which is August 15th. Okay, and notification to abstract applicants will be issued before September 1st. Okay, and also before the end of October. That will be the early registration deadline and also e-poster presentation submission. Okay, and since November 12th, that will be the beginning of the symposium, which is the tutorial workshop. Okay, next, please. So here are some sponsors so far. Okay, we thanks for the Ministry of Science and Technology in Taiwan, and also Ministry of Education, and also the IQVIA, Biotrice, SaaS company, and also some institutes in our Taipei Medical University, and also the hospitals, affiliated hospitals supports. Okay, next, please. So before the end, I would like to welcome all of you to come to Taiwan, and also join our symposium by using an online way. Both on-site or online will be welcome. And I would like to share introduction of Taiwan by using a very short video right now. And if you guys have not ever visited Taiwan, there will be a chance for you to come to Taiwan this year. Can you praise? Yeah. Jean, can you praise the slide?
Let me reshare because I need to include this, include the computer sound for that.
Okay.
And then let me see if I can do that. Okay, I've clicked on it.
Yes, click.
But it's not playing. So sorry, Jason, it's not.
Is that a slide? PPT file?
Yes, it's in the slide. Yes.
Let me share by myself. Is that okay?
Oh yeah, that would be great. Thank you. I don't know why it's not playing.
Please share the sound too.
Can you see the slide?
Yeah, it is.
Yes.
Can see.
Okay. Can you hear the voice?
No. Could you share it again, but including the sound, computer sound? If you click the share button, then there is a little button to include the computer sounds.
Where is it? I don't know. How can I?
It's not for your PowerPoint. It's on Teams.
Oh.
Yeah.
Will you click on the share?
Right.
Yeah. So if you stop sharing and then reshare, and then you can just stop
the X button. So you can click
Yeah,
the
the
X button,
And
and then
then-
re-click that button again. At that time, there is small button to include the computer sound.
on the first row.
Oh,
I don't know.
I had never seen it before. Learned something new.
Or maybe, cool. Yeah, we can see your screen.
And then right now,
Not your. We can see your screen, but not slides.
okay. Is that okay right now?
The screen is frozen.
Okay. I don't know how to operate. Sorry about that.
Or maybe we can just watch the video without the sound. I guess
Nope.
that's fine too.
The same from my point.
Okay, I think your screen froze. So Jason, how about that? If there's a link or anywhere on YouTube, I can help upload there and just share the link with everyone in the email afterwards.
Yes.
Okay.
No.
Cool.
No
Thank
problem.
you. And then I will. So I'll take the share back to the slides. But meanwhile, we can. So thank you so much, for, Professor Xu, to share the APAC. To share on the APAC Symposium that's gonna happen later this year in November. So I just want to, yep, I see Patrick and folks message in the chat. So definitely super looking forward to that. Any questions or any comments from the audience?
If you need a tutor of the tutorial, please remind me here.
Yeah.
Cool.
No, yeah, I will do that.
Sounds good. Thank you so much, Jason. So with that, and then we will be also sharing the video later on with the link. So that would be great. And then we'll go to the next part for our agenda today. Is we have invited Gowtham Rao to talk about and also demo to us how to create a cohort diagnostic tool for OMAP studies. So again, Gowtham Rao is a senior director from Johnson & Johnson, and he has been in the OHDSI community from 2016. So that means this year is the 6th year for you. That's amazing. And then without further ado, so Gowtham, would you like to start your presentation? Would you like to share?
Absolutely. Thank you so much. And I'm sharing my screen. Can you please confirm you can see it?
Yes.
Yeah, perfect. Perfect. Okay, I'm going to go to presentation mode. And there it is. And I don't like this. Okay, there you go. All right, thank you so much. So I'm going to be talking about COVID phenotyping. So for today, I got 5 topics that I want to cover with you. One is the project that's going on. I was invited to help with the project. That project has some cohort definitions. Cohort definitions to identify people with COVID-19. So we're going to be talking about those cohort definitions. There was a request to do an orientation to cohort diagnostics, the tool. So I'm going to also introduce you to the science of phenotyping, just a very early introduction. We're going to review the cohorts that were part of the study using cohort diagnostics. Then we're going to come to a conclusion of which is the best cohort definition for COVID-19 studies for this project. So that's the main agenda of this talk. So a quick background about the study. This is your study. The study is titled Comparison of Mortality, Morbidities, and Healthcare Resource Utilization between Patients with and Without a Diagnosis of COVID-19. So the goal here is to be able to identify accurately people with COVID-19. The study is in a SharePoint folder. So this is the folder, and I was given access to it. And that folder has 5 cohort definitions. These five cohort definitions that was reviewed and the number 5 was recommended by the group for this project. So the request is to run cohort diagnostics on these 5 cohorts and to come with an interpretation. So as part of this effort, about 10 days ago, I took these 5 cohorts and added it to a project. This was in an OHDSI studies repository called COVID Phenotype, and they're a branch for the ECSO COVID Phenotype. So it was added, it was executed on the 5 data sources by the Hong Kong University, and the results were shared back to as a network project. The 5 cohort definitions. This is my summary, my understanding of this cohort definition. So let me orient you to this slide. The number 1 column, the first column is an ID. They are the 5 cohort definitions starting from 1, 2, 3, 4, and 5. The IDs 184, 185, 186, 187, and 188 are something that the OHDSI Atlas for the Phenotype library assigned to these cohorts. The second column is just a name that I gave it. But the most important piece of information is what we call as logic description. So this is logic description explains what the cohort definition is actually trying to do. So going from the top to bottom, the first cohort definition, this identifies persons. It identifies the earliest date a person was tested for COVID-19 with a 365 days prior observation time requirement. And this test has to have been done on or after January 1st, 2000. So this was the testing for COVID-19. So if you are tested for COVID-19, you're in. That was the first definition. The second definition was the earliest date a person was tested for COVID-19 with a 365 days prior observation requirement on or after January 1st, 2020, with a positive test result between 0 to 7 days of the COVID test date. So they should have a test, and then within 7 days of that test date, they should have a positive test result. So if you have a test today and you get the positive result today, you're in. If you get a test today and you get a positive test result 3 days later, you're in. That's this definition. The third definition is the earliest date a person was tested for COVID-19 with the 365 days prior observation time requirement on or after January 1st, 2020, with a test positive result or a provider documented diagnosis of COVID-19 also within that 0 to 7 day window. So this is a COVID test followed by either a positive result or a provider documented diagnosis. The fourth cohort definition was the earliest date a person was tested with a positive result for COVID-19 or a diagnosis of COVID-19, and they had to have a 365 day prior observation time, and this had to be on or after January 1st, 2020. So the number 4 is got to have a positive test result or a diagnosis of COVID-19. And then the number 5, which is the one that was recommended by the group, was the earliest date a person was tested and found to have a positive result for COVID-19 or a diagnosis of COVID-19, but no negative COVID result within 3 days, and also with a 365 day prior observation window, and this has to happen on or after January 1st, 2020. So these are the 5 definitions.
So why do we need to exclude no negative COVID results within 3 days?
No, excellent question. So we'll go through that, Chang, in the next few slides. So this, I would, this is a study. These definitions were picked by the Hong Kong University team, and so this is a question for them. But I really like that they have done this, and so we explored this thing, and I'm going to talk about the value proposition, the importance of taking that, having that no negative COVID result within 3 days. In the next slide. So just hold that thought. So if you think about all those 5 cohort definitions, to phenotype somebody with COVID, we have various options. We saw several definitions that use labs. So you can have a cohort definition with just labs. You can have a cohort definition with just diagnosis. You can have a cohort definition which is lab and diagnosis. And you can have a cohort definition which is lab or diagnosis. So if you have a lab test, you're in. If you have a diagnosis, you're in. If you have a lab and a diagnosis, you're in. If you have a lab or a diagnosis, you're in. Along with that, for labs, you can also couple it with the results. And the results can be positive, can be negative, can be positive and negative at the same time. And it can be no result, just missing data. So all of this is possible. And but this is some work that the OHDSI Phenotype Development Evaluation Work Group had worked on. What you see is a very complex matrix. So I'm going to orient you here. In the middle, right here, is day 0. That's day 0. This is day -1, day -2, day -3, day -4, and day -5. This is day +1, +2, +3, +4, and +5. Each one of these is the testing in relation to some date. So this particular row are the people who had a COVID diagnosis, but they did not have any tests in the days before or after. The number 1 are people who had a positive test result. Number 2 are people who had a negative test result. And number 3 are people who had both positive and negative test result on the same day. So what you're observing here is we are seeing real people who have diagnosis followed by a positive test result. We're seeing people who have a diagnosis and at the same day, they have a negative test result. We have people who have diagnosis today and tomorrow they have a negative test result. We have people who have a diagnosis and a positive test result and a negative test result on the same day. And so all of this is observed in real world data. So we need to think about how to handle it. This is a real problem. This is not a theoretical problem. That is, we do see cases of people who are having this matrix. Now, when you look at the frequency tabulation, the last column is the frequency counts. And you're limited. The vast majority of this combination occurs within the first 15 rows and also within the first 3 days. And that captures pretty much majority of all the combinations of diagnosis, positive test result, and negative test result. So keep this idea in mind. This was work with the OHDSI Phenotype Development Work Group, and this is what they found. They said, now, the majority is captured in this range. Now, a similar work, just like the Hong Kong University, work was done at the OHDSI Phenotype Work Group, and they evaluated about 8 COVID phenotype definitions. And these COVID phenotype definitions were on the top, you had to have a diagnosis and a positive test result. You should have a diagnosis or a positive test result. You should have a diagnosis only. So they played with all these combinations of diagnosis and test, and this is all the results, all the cohort definitions. So as part of this study, the results which I'm going to share with you, we combined the 5 cohort definitions that the Hong Kong University shared, along with the cohort definitions that the OHDSI Phenotype Development Evaluation Work Group created. So we have a total of, I think this is about 12, then there's 5, so 17 cohort definitions were subjected to diagnostics and cohort diagnostics. So when we have this large set of cohort definitions, I like to think in terms of the sensitivity and specificity. What we have done here is an approach to just rank order these cohort definitions based on intuition or our general understanding. What is the most sensitive and what would be the most specific? So if I would tell you that a person who has a provided documented diagnosis and a positive test result on the same day is very specific. Would you disagree with me? And at the same time, if I say, if somebody has a COVID diagnosis or a positive test result, would you say that's more sensitive than the COVID diagnosis and a positive test result? And I think you would agree with me that the and would make it more specific, while the or would make it more sensitive. So this particular rubric here, we try to rank order based on our just intuition from the most sensitive, which is at the bottom, to most specific on the top. And what we are trying to do is to see if this intuition holds using Cohort diagnostics. So phenotype algorithms or Cohort definitions is one approach that we use, is our approach to classify people into groups which we are calling as cohorts. And we have a definition for cohorts, which is a cohort is a set of persons who satisfy a criteria for a certain period of time. And we define that period of time as cohort start date and cohort end date. But we know that there can be errors in this. Now, it's possible that the algorithm can identify people and say this person has COVID, but they may not have COVID at that point in time. Or it may say this person does not have COVID and they may have COVID. So we do have errors here. And we need to understand how much errors exist in these definitions. Because if we don't understand these definitions, then that's a threat to our science. No matter how much methods we use to adjust for biases, if there is misclassification errors at the phenotyping level, then our studies may not be reliable. So we have to look for misclassification errors in Cohort definitions, and we need to choose Cohort definitions that have the least misclassification errors for our study. So we have various measures for this. We have sensitivity, we have specificity, we have positive predictive value and negative predictive value. There's a numerical values that can be calculated, and we have methods to do that, including like the p-evaluator tool from OHDSI. But what is missing here is, although those tools quantify it, they don't tell us what is the source of these errors. Where is it coming from? And what can we do to reduce these errors? Like, how can we increase the sensitivity, or how can we increase the specificity, or how can we shift the index date misclassification? And that's what Cohort diagnostic tries to do. So we have proposed a theoretical framework for phenotype evaluation. This is a paper that was written, and Patrick is still sitting on it and is not moving it. So we're stuck. We have to get this paper out to publications. But this is a paper that we wrote and said we try to define what sensitivity error is for a Cohort definition, what a specificity error is for a Cohort definition, what an index date misclassification error is. Sensitivity errors. We may say that a given cohort has sensitivity errors if we observe evidence that there are persons in the data source who may have the phenotype of interest, but are not identified by the phenotype algorithm. Specificity errors. We may say that a given cohort has specificity errors if we observe evidence that subjects identified by the phenotype algorithms do not have the phenotype of interest. We can say that a phenotype algorithm has index date misclassification if we observe evidence that subjects identified by the phenotype algorithm have incorrect designation of event start date. So the third one is, if I say you have a person has COVID, the algorithm says the person has COVID today, but in reality they had COVID 2 days ago. That 2 days of difference in cohort start date is called index date misclassification. So I'm going to shift now to cohort diagnostics. So I'm bringing my screen here. I'm going to exit out of this slideshow, bring this one here, this one there. So this is cohort diagnostics. Slides. There you go. Okay. All right. So, so like there is a URL data.odyssey.org/COVID-19 APAC ACESO. This is your Shiny site that has the output of this study. There are 17 cohort definitions here. As the first step for the next 5 to 10 minutes, I'm going to just talk about the software cohort diagnostics. This is not a detailed cohort diagnostic demo. This is not a tutorial on it. If you would like to know more about cohort diagnostics, please come to the OHDSI Phenotype Development Evaluation Work Group and can spend one-on-one time and talk about this tool. But I'm just going to give a quick high-level orientation because it was requested. So cohort diagnostics is an R package. R package runs on person-level data sources that has been converted into OMAP Common Data Model format. It outputs a set of CSV files. Those CSV files are then presented to this Shiny application. It is the result viewer of cohort diagnostics. It has several menus here. Each menu is considered a diagnostic. And so each one of them has a specific purpose behind it. We have on the software few icons here. If you click on an icon, it will pop up and it'll provide you a description of what that menu item does. So there are various menu items here: cohort definitions, concepts in data source, orphan concepts, cohort counts, incidence rate, time distribution, index event breakdown, visit context, cohort overlap, 4 characterization tabs: cohort characterization, temporal characterization, compare cohort characterization, and compare temporal characterization. They all have specific purpose behind them. They help inform us with identifying sensitivity errors, specificity errors, and index statements classifications. So I'll go quickly over the cohort definition tab just to help you, just to orient you, and then I'm going to skip the rest and we'll go back to the slides. The cohort definition tab allows you to navigate and understand a cohort definition. So if I select the number 5 cohort definition, I can toggle through various submenu items here, and the one of the submenu will give me the count across all the various data sources that this study was executed on. This tab, cohort definition, allows me to understand what the actual cohort definition is and also export this cohort definitions JSON or SQL into another Atlas instance if I want to execute. It also provides me the concept sets that were part of this cohort, so I can explore it and look at the concept set expression. I can look at the resolved individual concept IDs and by using the drop down across the various data sources. There is the orphan concepts. Orphan concepts is a novel idea that was developed by OHDSI. This allows us, as an informatics solution that says, given a list of concept IDs that are part of your resolved and mapped set, what other concept IDs exist in the data that closely resembles the ideas behind the concepts that you have selected? So for example, suspected COVID-19, SARS-CoV antibody panel. These are something that the orphan recommender is bringing forward to you. But when we review it, I would say this is not these concepts you would not want to add to your concept set expression. But it brings forward these just to make sure that you don't miss any codes or concept IDs. So I'm now going to go back to the slides here and just walk you through the slides. So remember, we have 5 cohort definitions as part of the Hong Kong University project. The number 5 is the recommended type. We try to describe the different cohort definitions. The main idea behind the main difference between the first 3 cohort definitions and the last 2 cohort definition is what the entry event criteria is. The first 3 cohort definitions require a lab test to be the entry event criteria. The 4th and the 5th one says you can have a lab test or a diagnosis. That's the key distinction. Now let's apply that logic of those 5 cohort definitions and look at the cohort count menu item in cohort diagnostics. The study was executed on 5 data sources by Hong Kong University. the UK IMRD data source, US Open Claims data source, France LPD data source, Germany DA, and Italy LPD data source. So you have those as 5 columns, and then the 5 cohorts are row items. When I look at this, I use a rubric to evaluate the output of cohort counts. The main rubric, the set of questions here are for cohort counts. Are there phenotype algorithms with cohort count of 0 in some data sources? And as soon as I see the cohort count menu, I see lots of zeros. There are zeros for France LPD, Germany, and Italy LPD. The question is why? Why do these data sources have 0? It turns out that these data sources may not have any labs. In fact, these data sources don't even have a lab testing documented. Now, US Open Claims data has 21 million records for the first cohort, the C13 cohort. The C13 cohort happens to be a testing for COVID-19. Testing for COVID-19 just says you've been tested for COVID-19. It does not tell you whether you have a positive or negative result. It just needs you to be tested. US claims data has procedure codes for testing, that the procedure codes are not coupled with a result. So US Open Claims data has 21 million individuals who have been tested for COVID-19, but it doesn't have any results. So we don't know if there is positive test result or negative test result or missing. France LPD, Germany DA, and Italy LPD does not even have testing documentation, which I found is interesting. So it's something that we have to ask, is it really true that they don't even have documentation of a test performance? Now, UK IMRD does have a significant amount of test performance at 416,000. The second cohort definition, to the C14, couples the performance of a test with a positive test result. As soon as you require the positive test result, 4 of the 5 data sources are out, because they're just giving you 0 counts. US Open Claims does not have any results, it looks like. France LPD, Germany DA, and Italy LPD does not even have testing, and they obviously does not have any results. UK IMRD, the number of people who were tested was 416. Out of that, 23,882 were considered positive. So it is identifying 23,000 people. So the only data source of the 5 data sources that got any hit with a lab test result was the UK IMRD. An important insight right off the bat. So it basically says the cohort C, the definitions, the first 3 definitions that require the lab test as an index date is out. It cannot be used for a study unless you just want to study it on UK IMRD. Right? So let's go to the next insight. So we have in this particular slide, I'm presenting to you the cohort definitions that were part of the OHDSI work group. So we got 5 cohort definitions here. And what is interesting here is at the bottom part, all of these cohort definitions are giving the exact same count. They're not the same cohort definitions. They're different cohort definitions, but they're giving exact same count. That's interesting. That's especially for France, Germany, Italy. And that's basically because this is all the provided documented diagnosis of COVID-19. The lab's not making any difference. It's all diagnosis. And because all of these are basically diagnosis with some variations of lab tests, that's an OR. So if you have a diagnosis, you're in, or if you have a lab test positive, lab test negative, then you're in. The OR is just bringing people with a diagnosis. So you have a lot of people with diagnosis. Now, so what we have is as an insight is for majority of the data sources, lab doesn't matter because everybody's coming in through diagnosis. France, Germany, Italy, JMDC, Truven, CCAE, Truven MDCD, Truven MDCR, and US Open Claims. For all of this, if you have a diagnosis, you get record counts. If you add a lab result, it doesn't matter. Lab doesn't matter for these data sources. It doesn't have any. But What we also can see from cohort diagnostics is labs are important. If you have a data source with labs, that makes a big difference. For like CPRD, here we have two cohort definitions. The first row, which is C1, is diagnosis only. The second one is diagnosis or a positive test result. And look at the difference in the counts. In the CPRD data source, there are 33,000 in the first cohort, which is diagnosis only, but 280,000 in the test or positive result. That's a huge difference. In Optum EHR, which is the electronic health record data source, there is about a 15 to 20% gain, 759 versus 951. In Optum extended DOD, it goes from 1.4 million to 1.6 million. And in the UK IMRD data source, man, that's a huge gain, 8,000 to 31,000, and that's your data source. So it's important. In some data sources, it doesn't matter, but in others, it's important. Now, what is interesting here is it's an insight that we have. It's a reverse interpretation. What we can interpret from this is in the data sources that don't have lab results, we're having sensitivity errors. Why? Because what we're observing in these is there are people who are positive only by labs and they don't have any diagnosis. So if you have in CPRD 280,000 people, and after 280,000 people do an intersect of 33,000 people with diagnosis, that leaves 250,000 people that could identify just by lab. So there's a lot of people with just labs. Same thing with Optum EHR. There's about 150,000 people. There's 100,000 people in Optum DOD, and there's about 24,000 in UK IMRD. All of this is telling us is there are people in the data sources that are identified to have COVID-19 just by labs, and even then they do not have a diagnosis of COVID-19. So the other data sources, the Truven CCAE and France LPD, Germany DA, it has missing information. It has sensitivity errors because it does not have lab results. People are being observed to have disease, just labs. So the main insight is if you want a cohort definition, we need to use an OR criteria. We need to use a test or condition. We can't just do test, cannot just index on test and require a diagnosis. We should index on either test or condition. Now, so this of the 5 cohort definitions that the Hong Kong University proposed based on cohort diagnostics using the sensitivity errors check, the first 3 are gone. They do not pass diagnostics. That leaves 2 cohort definitions, C16 and C17. C13, 14, and 15, the 1, 2, and 3 have essentially failed sensitivity errors diagnostics. Now, are there? So I made a statement that there are people who are observed who only have diagnosis and no test result. There are people who only have test result but no diagnosis. We observed that in our previous slides. But are these two different? So UK IMRD data, what we are doing is we're comparing 2 cohorts. One cohort are people who just have diagnosis. Another cohort are people who just have a positive test result. So we are comparing people who have diagnosis only to who have a diagnosis with those who have a positive test result. And what we're observing is they're very similar. So from a characterization standpoint, the population that have just test result is very similar to the population that has diagnosis. So this is a temporal diagnostic of cohort diagnostics. On the right side, we have one slide here, which is on the index date, day 0. So these dots here are basically that this person was tested for COVID-19. Well, that's because it's part of the criteria. What is the definition? This one here is the diagnosis of COVID-19. One cohort it requires everybody to have a diagnosis. But other than those dots, everything else is right in the middle. Same thing in the period immediately after, in the first 30 days after the index date. What we're observing is that the two cohorts seem to have similar experience temporally after index date. So it makes us conclude that they seem to be similar, or there may not be any difference between these two cohorts. So they're similar. So now we started with 17 cohort definitions. Right off the bat, the ones in the red have failed our diagnostics. They have failed the sensitivity errors. That's because they're indexed on lab tests. We need core definitions that use an or clause. You have a diagnosis or a test result. So now we have two core definitions from the ACSO study, the COVID 4 and 5, and 4 definitions from the OHDSI Phenotype workgroup that are candidates for further evaluation. But to compare this further, we'll require data sources that have lab results. So now we're going to look at data sources that have lab results. We have 4 data sources that have lab results, and here is the 5 cohort definitions, 5 candidate cohort definitions. In the CPRD data source, the cohort counts pretty much similar. The last two, C16 and C17, are the ones from ACESO, while the first 4 are from OHDSI Phenotype workgroup. Similar, but the ACSO has lower counts, 271, 261, compared to 280. Maybe an indicator of sensitivity errors. In Optum chart, 823, 772, 900,000 plus. Again, a sensitivity error indication. A big drop here, 1.2, 1.14, 1.5, 1.6. Same thing at 29,000. Oh, this is a plus 35,000. Interesting. But we see a difference. But they're similar. So, but they're all similar in sensitivity, not a huge difference. There's some drop. So we're done with sensitivity errors. Now let's go to specificity errors. We have defined specificity errors. So how do we look for specificity errors and try to select among the 5 cohort definitions? Remember, we have this problem of people having multiple test results, and some people even having a positive test result and a negative test result on the same day. So we have to handle that. And when we don't know what the impact of handling that is, does removing people with a negative test result, actually, like Chang asked, does it improve our specificity? That's the question that we're trying to answer. By people that have a negative test result different from the rest of the people. So we are now comparing. Which one is this? This one must be. Yeah. So this is people with a positive test result. People. It was one of the core definition is people with a diagnosis or a positive test result. The other one is people with a diagnosis or a positive test result, but no negative test result within 3 days. So this is the comparison that we are trying to do. One group has diagnosis or a positive test result. The next group has a diagnosis or a positive test result, but no negative test result within the 3-day window. What we're observing at baseline, there's no difference. They're pretty much the same. We observe in the first 30 days after, pretty much the same. They seem to be identical. So it looks like, based on these slides, it doesn't matter. You can choose either one of those and you're still fine. We had run by one data partner. We found that in Columbia University Medical Center, it was different. So we're like, when we observed that, we were thinking about it and said, okay, there seems to be some difference. Why is that? Let's explore it further. Majority of the data sources, there was no difference, and we were about to conclude no difference, but one data source showed a difference. So to solve it, what we did was we built a marginal cohort. So we built a cohort of people who had a COVID diagnosis or a positive test result, and compared with people who had a negative, who had a COVID diagnosis and a negative test result. And that basically showed us huge differences. There was a big difference between the people who had a diagnosis or a positive test result compared to diagnosis and a negative test result. So having a negative test result showed us differences both at baseline and in the temporal periods afterwards. So big differences. Look at the deviation. So it basically helped us understand that people who had a diagnosis and a negative test result may not be having COVID, or they're systematically different from the people who have a positive test result. So they have to be removed. By removing that, it improved our specificity. The counts of these people were very, very low. So from an overall, if you remember here, removing it, C16 versus C17, the counts was not much. The percentage of count that we lose by removing people who have a negative test result was like less than 1%. So your loss in sensitivity is not much, but the improvement in specificity, oh my God, look at that improvement in specificity. So that's what Cohort diagnostics just enabled us. So by using this way of thinking, we were able to empirically go and say, it makes sense. So what's the recommendation? You're on the ball here. Cohort definition number 5 is the right cohort definition. You need to have a provider documented diagnosis of COVID-19 or a COVID-19 positive test result with no COVID-19 negative test result between 0 to 3 days. The only additional recommendation I would do is I would recommend you to use the OHDSI definition versus this definition. The reason is you're getting a slightly more sensitivity with the OHDSI definition. So that's the evaluation of this definition using cohort diagnostics. So I'm open to any questions, or we can have a discussion.
Great, thank you so much, Gowtham. I know we have about 5 minutes left. I don't know, I know the Hong Kong U team and other study owners, the participant, anyone have any questions for Gowtham?
Gowtham, just on that last point you just made about the recommending the OHDSI definition, what's the key difference? What's the critical difference there?
Yeah, so the main difference was the 365 days observation time, I think. So the 365 days observation time, is there a real need for the 365 days prior observation time in the context of identifying people with COVID-19? So it depends upon your thinking behind it. When we were thinking in the OHDSI work group, we thought we want to identify people with COVID. It's a new disease. Well, how would the 365-day prior time help us? Requiring the 365 days prior observation time, you're losing people. I think that's the main difference.
So it's interesting though, isn't it? Because I guess having that criteria might help with not losing people. But if you want to use the characteristics to, do something on that cohort, you actually do require that 365 days, right? So it's a trade-off.
That's absolutely right.
Yeah.
That's absolutely right. So there's really no perfect answer, right? Every cohort definition, every phenotype algorithm comes with its own trade-off of sensitivity, specificity, and index statements classification. What we just did was we surfaced it out. Now, depending upon your study's realities, you want to accept some of these trade-offs. So if baseline characterization is important, and you want to allow the person to have 365 days prior observation time to accumulate those baseline characteristics, then it's important for you, and then you accept some sensitivity errors because you know you're losing some people with COVID-19, but that's okay because that's important for you for your study context. So phenotype development evaluation has to be done independent of the study context. It just surfaces the potential misclassification errors, and you choose which misclassification errors is acceptable for you for your study.
Yeah, got it. Such an important point.
Great,
Hello,
thanks.
Gowtham. Sorry, Jing. This is
Go
Ivan
ahead.
from the Hong Kong U team. Yeah, first of all, thank you for giving us this wonderful presentation and also your effort in developing the cohort definition package. I still have a few questions on how you were able to increase the specificity of the cohort definitions by looking at those graphs. I'm not sure if you can go through it again on this point specifically, or whether I should contact you afterwards to get the answer.
Yeah, so the general idea of improving specificity is to remove people from your cohort, those who you are pretty sure do not have the phenotype of interest, right? So you want to remove people that do not have COVID from your COVID cohort. So the question is, are people who have a diagnosis and a negative test result at almost the same time, do they have COVID or not? What we observe here from this last slide is they are different. They are the people who have a COVID diagnosis and a negative test result are different from people who have a COVID diagnosis and a positive test result. When they are different, they're more likely to not have COVID. And that's where we are stretching it. And so we're saying these people are different, so they may not have COVID. So we're going to take them out. So when we say that they are different and they are most likely not having COVID and we are taking them out, that improves your specificity. Does that make sense?
Yeah, am I correct to say that the X and the Y axis represent different cohorts definitions, and if they are different, then there's potentially a specificity error?
Yes. So yes. So I should have probably oriented you all to the slides and what they mean with the axis. So here in this particular case, this is one cohort and that's another cohort, and it is looking at one time window here, and each of these dots are covariates or features about the persons that were in the cohort. So you have the proportion of that covariate from 0 to 100%, and the proportion of the covariate from 0 to 100%. So each dot, so this particular covariate was probably 35% in the C85 cohort and 20% in the C48 cohort. So that's what it means. So this dot here would mean that that particular covariate is pretty high in the C85 cohort and very low in the C20 cohort. Might actually benefit by doing a live showing here. So if I go to compare temporal characterization, and I will select, let's say, UK. I can't do it here because I don't have that marginal cohort. But let's see. So select these drop downs. Select one of these. Let's make it COVID diagnosis only. Another one will just for illustrative purposes, COVID positive test result. And this is how the plot is generated in the tool.
Yeah, thank you very much. That's very helpful. Yeah, I think I'm gonna have a look into this result website and yeah, and let you know if I have any further questions. But thank you very much for the presentation.
Cool. Thank you so much, Gowtham. I know we're a bit over time, but that was super great and helpful. I know we're a bit over time, so feel free to message or let us know if you have additional questions for Gowtham or on the cohort diagnostic in general. And so that will be all for today's community call. Thank you guys so much. Have a good one. Thank you.